Okay, if you take a look at Rolle's theorem, think about what we've done. The extreme value theorem, that was 3.1. What did it say? If you got a closed interval and the function is continuous, you're going to have a minimum and maximum on that interval. That's all that was saying. And that's what 3.1 was about. Rolle's theorem takes that a step further and says, okay, if you've got a continuous function on a closed interval, same kind of deal, and it's differentiable on the open interval. Now notice the open interval does not include the endpoints. Then there's at least one number in between these two values, a and b. There's at least one number, c, that's an x value, that has what? Has a derivative that's equal to 0. Now, what does that tell you? If the derivative is 0, what does it tell you? That means the slope, you've got a tangent line that has a horizontal slope, right? That's what that means. And so Rolle's theorem says we've got a continuous function, could be a straight line. Yeah. What if it was a horizontal line? Is there at least one point in between those two endpoints that has a slope of 0? That's right. It's all slope 0. Exactly. You're exactly right. All right, so that's what it's telling us. So look at this visualization. I mean, this set of notes is pretty sparse. So most people, when they're thinking of rolls, they're thinking this top drawing up here. This D is the Y value of these 2 points. So this point on the left is what? The X value is A, the Y value is D. On the right-hand end, we've got a point, the X value is B, the Y value is D again. That's the picture everybody has in their mind of Rolle's theorem, and that's a good one because somewhere up here, we've got a relative maximum.
But is that a straight line? Is that at one singular point?
That relative maximum is at one point. That's where the tangent line touches that curve. And that's what Rolle's theorem is talking about. Now then, that's with the requirement that that function's differentiable. Is this bottom one? No, because it's a function.
It doesn't curve like the top one.
Think in terms of limits. Does this top point up here, is there a limit? I hate to use the L word, but limits. As I'm approaching that top point from the right, is the limit the same as from the left? No. So it's not differentiable. On the top one, as I'm coming up from the right side and from the left side, I'm approaching, the slopes are the same. I mean, they're approaching the same limit. All right, so it has to be differentiable. So look what this first little question is saying. It says, find the roots of this function. So the first thing I'm going to do, no, just the roots. Where does it cross the x-axis? So I write my function down. I can factor it. And so then I can get my x values. So that means what? That function crosses the x-axis at 1 and 2. Now, what's Rolle's theorem saying?
At some point between 1 and 2, it's a straight line.
And we can say that because why? 1 and 2 have the same y value, right?
Yes. 0.
0. So now what do? Now I've got to get the derivative.
2x minus.
Okay, so there's my 2 points. So I'm going to say, there's my points. And I'm going to get the derivative. Check my math.
Good.
All right, so now that I'm going to solve that derivative for x. And we get to here, finally. So in between the points 1 and 2, specifically where x is 3/2, that thing's going to have a y value that at that y value, the slope of the tangent line is going to be 0.
Last homework, that would have been a critical number.
Yes, exactly.
So what variable would make it a critical number instead of a straight line?
If you think back at 3.1, it said what? Every place the derivative is 0 is at a critical number, but not every critical number is a tangent line with a slope of 0. So it's sort of like saying, well, if it's a dog, it has 4 legs, but you can't turn around and say, if it's got 4 legs, it must be a dog.
So a critical number can be a Rolle's theorem, but not all critical numbers are Rolle's theorems.
Rolle's theorem is saying there will be a critical number that marks where a horizontal tangent line exists. Now think about it. If the horizontal tangent line is there, doesn't that mean it's either a minimum or maximum?
Yeah, that makes sense.
Okay.
Oh, there. I was thinking that when you talk about a straight line, that the slope itself was a straight line, not the tangent, not referring to the tangent line.
Yeah, just the tangent line. And if you watch the video, where's the x value of the vertex of that parabola? Because that's a parabola. The x value is 3/2. Okay. We good? So that's saying where x is equal to 3/2, we've got a horizontal tangent line. So it's like the top picture. It's like the top picture. If this point right here were 1 for my x and this point were 2, then this would be 3/2. That's all it's saying.
What do we need the reach for if we just needed to find the tangent?
It wanted you to see that the point 1, where x is 1 on this function, when x is 1, the y value is 0. When x is 2, the y value is 0. And if you go back and look at Rolle's theorem, it says they have to have the same y value. F of x1 equals, or f of a equals f of b. That was part of it. Okay, let's keep going. So here's another one that's kind of in the same vein as Rolle's theorem and the extreme value theorem. This is called the mean value theorem. Just take a look at it. This is more specific than Rolle's. Notice we got to have a continuous function on a closed interval, and it's got to be differentiable in that open interval. Is that anything different from Rolle's setup? No. This is saying there's going to be some number in that interval, some x value c, where the derivative of c, or the derivative at c, is the same as if you just drew a line in between 2 points on there. If we got a straight line slope, that's easy to find. We've had a formula for that forever. All right, so let's look at this one. Here's what it's saying in just plain old English. If you get the average slope between 2 points on that continuous differentiable function, then there's going to be some point in there that's going to have the exact same slope at that point.
just so I know what you're talking about, the f of b in the theorem 3.4 just means the y coordinate of b, right?
Exactly.
Okay.
This is sort of like saying, well, if I'm in the United States and I end up in Canada, there's some place where I crossed over the line. This is saying if you're going from A to B and you connected those points with a straight line, that line's going to have a slope. There's somewhere in that function of A and B, no matter how curved it is, that function going from A to B, no matter how curved it is, there's going to be at least one point that has that same slope. So look at this example. I think it'll help you see it. So, kinda, it all plays in. So what I'm going to do, this is saying the interval is from 1 to 4. So the x values are going from 1 to 4. So I'm going to find the y value when x is 1. So that's what I'm doing here. So my first point is at 1, 1. Does that make sense?
So the 1 and the 4 are just 2x, so I'll use them at x and y.
Those are 2x values. Yeah, that's kind of confusing when you see it until you realize, oh, that's the given interval they're talking about. So then I'm going to do the same kind of thing for my second point. So the x value is 4. I just plug 4 in to get my y value here. So that means my second point is at 4, 4.
So the equation would be...
John, you with me?
Why is it 1 and 1?
Because if x is 1 right here, then the y value for 1 is 1.
The equation would be 4 minus 1 over 4 minus 1.
Yeah, so I'm just going to sketch this out. And I'm going to put those 2 points in, and I'm going to connect them with a line. So that's the situation we're talking about. I don't know how curved that thing's going to be. I know that that function, having 4 over x, when x is 0 there, it's not going to be a continuous function, right? It's going to go to infinity. So this is not a straight line function. But I can connect these 2 points, 1, 1 and 4, 4, with a straight line. Well, what's the slope of that line? I do the old formula, y2 minus y1 over x2 minus x1. And like the man said, the slope's 1. So what's the mean value theorem telling us? Is this differentiable on that interval? Yeah, because x is not 0 on that interval. It starts at 1 and goes to 4. So it's differentiable. Is it continuous?
Hey, can I clarify something? Is C referring to a slope or a point on the graph?
For what?
Like f of C. This was the equation for f of C, right? F of B minus f of A over B minus A. Is f of C like a point on the slope on the graph or slope?
It's a point on the graph. C is just another x value. And f of C is whatever y corresponds to that x value.
We ended up getting 1 at that.
Well, the slope is 1.
Yeah.
Because we took those 2 points and did our slope formula here, just for straight lines that we started, in 7th grade or 8th grade or whatever.
But isn't the slope formula the same as the mean value theorem?
No, the mean value theorem is saying somewhere on that curve, there's a point, there's an x value that at that point, the slope of the tangent line is 1. So now what do we have to do? We have to find that point. So how do we do that? Well, I'm going to rewrite the function in that form. It's the same thing, but it just makes it easier to see what's going on when we differentiate it. Which equals this. Now, again, we're not talking about 0, because that would make the derivative not defined. So what do we got to do? We got to say, all right, here's my derivative, 4 over x squared. That's the equation. Remember, f prime is a function. The derivative is a function. All I got to do is set that derivative to what? 1. And then I got to solve for x. And we finally get down to exactly. And if you saw a graph of this, both of those are true. But we're only worried about the interval from 1 to 4. So it's the 2. So when x is 2, I've got what? The slope of the tangent line is 1. And that's what the mean value theorem is saying. Yeah, but we're only interested in this interval.
F prime of C equals.
Yes, yes. You might want to put a star by that. So far, so good, y'all? Okay, we're to 3-3. So if you start thinking about 3-1 and what we just saw in 3-2, we're getting those relative minimums and maximums. How did we do that? We used the first derivative. So this is about the first derivative test and whether a function's increasing or decreasing. So basically, look at the definition there. That's the technical definition. Very mathy. The one we're probably used to is this one. Take a look. As x moves to the right, if the y values are going up, the function's increasing there.
Makes sense.
Yeah. This is not the technical definition, but it's the one that makes more sense to us. As the x values are going to the right, if the y values are going down, the function's decreasing.
I follow you there.
Good. And so we're looking at this picture here, this graph, and it's saying, it's illustrating that very thing, decreasing, increasing. But what if as we go to the right with the x's, the y values stay the same? Then that's that middle chunk in there.
The constant.
Yep. But the important thing is, what are the derivatives doing on that left-hand side? Yeah. Remember, we got tangent lines all the way down this. What's their slope? Positive or negative or 0? Negative. And so when the function's decreasing, that means the derivative is negative. When the function's increasing, those tangent lines are all going to be sloping up. So if the derivative is positive over an interval, you know the function's increasing there. And if the derivative is 0, guess what? It's constant. Okay, and so here's the test. What's it saying? If f prime of x, so if the derivative is greater than 0, meaning positive, right? Yeah, exactly what we just covered. Well, let's keep going then. So here's the plan. We're going to find the derivative. We're going to find the critical numbers. And we're going to decide, okay, what's the derivative doing in different intervals? So I've got x cubed minus 3/2 x squared. I want to know just where it's increasing and decreasing. So I get the derivative. So I'm writing it like that. I'm pulling that 3/2 out because it's just a constant. So I can cancel my 2's. And that gives me that for my derivative. So far, so good. Now what do I want to do? I want to find the critical numbers. So I take that thing, set it to 0. And in general, I don't want to cancel a bunch of stuff out if it has a variable in there because I'm going to lose one of my results. Yep, I'm just going to cancel out the 3's. I can do that. So that leaves me with x squared minus x equals 0. And again, I don't want to move that x over to the other side. I just want to factor out x, which gives me 2 factors. We're back to that college algebra idea. Oh, if you've got 2 things multiplied together and they equal 0, you can set each one of them to 0. So that's what I'm going to do. And when I do, I'm going to get one of my values is 0, one of them's 1. Any other critical numbers there? We don't have a denominator. So those are our critical numbers. Next thing. I'm going to use those critical numbers to divide the number line into 3 chunks. Like that. Now I want to test that left-hand chunk, the middle chunk, and the right-hand chunk. And we did something like this in college algebra and in pre-cal, as a matter of fact. So I'm going to pick a value to the left of 0 and between 0 and 1, and these are ones I picked. Doesn't matter as long as they're in those intervals.
The same thing you do for the maxima and the minima. Extrema. You pick.
Yeah. Okay, so now I'm going to take each one of those numbers I wrote in blue, and I'm going to test it over here with my derivative. And I'm just going to use, all I want to know is the value I get positive or is it negative? I don't need to know exactly what that number is. So here's what I'm thinking. If x is -1, then over here in my derivative, I'm saying a negative number on the outside. What am I going to have on the inside? Positive or negative here? Negative. So it'd be -1, -1, so that's -2. So I've got a negative times a negative. What's that going to give me? So what does that tell me about this chunk? Yeah. So from -infinity all the way up to 0, but not including 0, that function's increasing. I'm going to do the same thing with the 1/2. Here's what I'm getting. If it's a positive 1/2, I've got a positive number on the outside. What do I have on the inside? Negative, right? Positive times a negative gives me a negative, so I know that middle part is decreasing. Now be thinking about this. If the slope is going up to the left of 0 and it's coming down to the right of 0, what kind of thing is 0 going to be? A minimum or maximum? Slope's going up, it gets to 0, it turns around and starts coming down. Maximum. We don't even have to see this function to know that. I'm going to do the same thing with the 2 out here. If 2's on the outside and then on the inside I've got 2 minus 1, positive. So here's where my function's increasing. On these 2 pieces, right? The left-hand side, the right-hand side. Those are not connected. So how do I say I want to tie those together? I'm going to do it with this union symbol. Remember, it says this piece or this piece. That U means or. And it's decreasing in the middle there. Think about the point 1, where x is 1. the slopes are negative on the left-hand side, positive on the right-hand side of it. What does that make one?
Minimum.
A minimum. Here's the guidelines. We just went through them. So we found the critical numbers. We did that. It says use these to determine the test intervals. Okay, that's where we divided the number line up into chunks. Then we just got values in each one of those chunks to see what the derivative was doing, whether it was positive or negative. And it tells us at the bottom, this works even if you're talking about intervals from negative infinity, positive infinity, stuff like that. Here's a definition you may or may not have seen before. If we look at this cube function on top, it's monotonic increasing. There's never a place on that cube function where it's not increasing. Zero, it's going through zero, but it still it's increasing the whole time.
If on that last equation.
Contrast it with the bottom one down here, where it evens out.
On the last equation.
This one would have a constant for the derivative there.
Like these. They're one from the constant.
You're losing me.
Like.
If you look at that bottom figure, it's increasing. It never is decreasing. So that would be an increasing function. But it's not strictly increasing because just what Wyatt said, it evens out in here. And look how that function is defined. It's a piecewise function.
Can we get a constant in one and a function that isn't piecewise?
Probably. I couldn't tell you one right off, but probably. That first function we looked at, you know, where our critical numbers were 0 and 1, here's a picture of it. And we had already figured out that where x is 0, that was a relative maximum, and where x is 1, it's a relative minimum. So down here in the highlight part, it says, well, this makes deciding what are minimums and maximums a lot easier, knowing this. Let's take a look at some. Here is the official first derivative test. Just look at it with me. Where do you have a relative minimum? Well, where the slopes are going from negative to positive on either side of it. Where do you have a maximum? Just the opposite. What happens, though, if you get a critical number, but the slope doesn't change? Actually, what it means is it's not a minimum or maximum. It can have a horizontal slope right there at that point. Probably does. But it's not a minimum or maximum.
I suppose theoretically it doesn't have to be a constant. It just briefly smooths out and keeps going.
Yeah, if it keeps going at the same y value, though, it's a constant. Yeah. Okay. So you could have a critical number. That's what those bottom two pieces are showing you. You could have a critical number where the slope doesn't change from positive to negative or vice versa. All that means is it's just not a minimum or maximum. It's still a critical number. So we got our critical points. If you see a sign change at one of those critical points, you've got either a minimum or maximum. If you don't see a sign change, like those last two, then you don't have a minimum or maximum. So the notes are telling us, oh, this comes in handy if you're sketching curves. It also comes in handy if you don't have a graph of a curve, you know what's going on at different places. And that mentions the position function and velocity and acceleration, all that sort of stuff in physics comes in handy. So let's work a couple of these. So notice we're talking about the interval from 0 to 2 pi. Don't you just love these trig functions?
Yep.
So I get the derivative. Am I good there? Now we have to find the critical numbers. All right. Anything making that derivative not defined that we can tell? No. So I'm saying, all right, where is cosine x equal to 1/2? So it's unit circle time again. I know in quadrant 1 it would be positive 1/2. Where else?
Quadrant. 13.
Or 4. Cosine and secant are positive in quadrant 4. Remember that cast thing? Okay. Sine and cosecant positive in 1 and 2, tangent and cotangent positive in 1 and 3. So we're talking about quadrants 1 and 4 here. And since we're going over 0 to 2 pi, I need to consider those in the things in quadrant 4. So equals 1/2 at pi over 3. How do I know that? Well, that left-hand trick. Cosine, where would it be 1/2? I put this finger down. Right? That's pi over 3, 60 degrees. So pi over 3, where else? Well, here's a trick. Keep the denominator 3. You know it's going to be 3 because of the reference angle idea. In quadrant 4, what else do we know? We know the top number is 1 less than twice the bottom number. So 5 pi over 3. At both of those spots, those are critical numbers. So what do we do? Same thing we did before, except now we're using angles. So I've got to pick values, and this can get interesting sometimes. I've got to pick them in those different places. So I'm picking pi over 4, pi, and 11 pi over 6.
What about your interval, the 0 to 2?
That's the whole interval that we're talking about. Over that whole interval, we only had 2 critical numbers. Good question. Okay, so I plug pi over 4 into this thing right here. So I've got 1/2 minus the cosine of pi over 4. What's the cosine of pi over 4?
I'm supposed to be dismissed at 10:45.
See ya. See you tomorrow. Make sure you watch the rest of this, Wyatt. Enjoy lunch.
Thank you.
Cosine of pi over 4. Pi over 4's that one down. Right? Cosine is square root 2 over 2. So I've got 1/2 minus the square root of 2 over 2. Y'all, we don't have to figure out the exact number. Is that going to be a positive result or a negative one? Which is bigger, 1 as a numerator or the square root of 2 as a numerator? Square root of 2, because it's 1.4 something. So I'm subtracting a bigger number from a smaller number, so that means I'm getting a negative result, which means negative slope. So anything from negative infinity up to pi over 3, actually anything from 0 here to pi over 3 is going to be decreasing. I do the same thing with pi. What's the cosine of pi? Negative 1. So I've got 1/2 minus a minus 1, which is a positive number. So I know this middle part is increasing. Now, this one is going to be in the 4th quadrant. What's it going to work out to? That. I've got a bigger number from a smaller number, so that's going to be negative. And that's the way it looks. So is this asking us to find, the extremum? So what do I know? Here's my critical number. It's going from a negative slope to a positive one. So that's a minimum. From pi over 3 to 5 pi over 3. Or at 5 pi over 3, I should say, is our relative maximum. You can graph that thing. I suggest highly that you get into Desmos and graph not only the original function, but the derivatives. You will learn a lot from that. I wish they'd had Desmos when I was learning this stuff. Okay. Another one. So first find the derivative. Oh, chain rule time. So I'm getting this. I need to start cleaning it up a little bit here. I think that's what it would come out to be. It is. Which I could then rewrite like this. So check my math. So now what? This is a rational function. That means I've got to treat the numerator separate from the denominator. I want to know where that numerator is going to be 0. So I take the numerator, I solve for x, and I get, at the point where x is 0, the numerator is 0. So there's a critical number. The denominator, I don't have to figure all that junk out. I need to go, where would that make that fraction, that derivative, where would it make it undefined? And so I take what's inside that square root or cube root, and I set it to 0. All I'm interested in is the x squared minus 4. And like the man said, what am I going to get? Plus or minus 4, so plus or minus 2. Do I need to know both of those here? They didn't give us an interval. Yeah. So I've got 2 more critical numbers. So I've got 3 critical numbers. So that's going to divide our line into 4 parts, sorry. There's my critical numbers. So I'm going to pick values in each one of those segments. I'm going to pick values to make things as easy as I can. I'm not going to use fractions if I can keep from it. So I start plugging them in. And I'm just going to go with my reduced derivative over here. If I put a -3 in there, what do I have on top? A negative number. What do I have on the bottom? I'd have -3 squared, which is 9, minus 4. That's a positive number, which gives me a negative. So I know this leftmost piece is decreasing. I don't care about the actual values. I take the -1. On top, what do I have? Negative number. On the bottom, what would I have? -1 squared is 1, minus 4, that's a negative. And your first reaction is, well, that's not defined. Yeah, it is for cube roots. We're talking about a cube root here. Negatives are fine in cube roots. So I've got a negative divided by a negative, positive, so I know that second piece is positive. So what do you think about -2? Is it a minimum, maximum? Minimum. I stick a 1 in there. Now then, the only thing that changes on this as opposed to the -1 is that top is positive. The bottom is still negative, isn't it? So that gives me a negative here. When I plug a 3 in, I've got positive 12. And I'm back to 3 squared is 9 minus 4. That's a positive number, which gives me a positive and gives me a positive out there. So I know that I've got a relative minimum at negative 2. I know at 0, I've got a relative maximum. And we've got another relative minimum out here at positive 2. Again, if I were you, I would graph that original function in Desmos. If there's some things you don't know how to do in Desmos, get with me. I'll sure show you. Okay, one more, and the notes are done. Dun, 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 dun. Quotient rule. So I get the derivative. So I've got the bottom function times the derivative of the top. Minus the top times the derivative of the bottom. And then I square the bottom. So I'm going to simplify this a little bit. I just multiply it out because these are just all powers of x, it looks like, except for that 1. I'm getting this. All of that's over x to the 4th, like the man said, which gives me this. This is a rational function again. So what do? Separate the top and bottom. So for the numerator, I set it to 0. I can just do this if I want to. I'm going to treat each one of those factors, set it to 0. So there's one of my critical numbers. They didn't give us an interval on this one either, so I get my other value here. I want to know the other factor in the numerator is this, so I'm going to solve for x. So there's 2 more critical numbers. Will we leave anything out? The denominator. If x is 0, we got a problem, right? What do you think is going to happen when x is 0? What's our function going to do? What's our derivative doing? Is it defined? Yeah, you'd have 0 over 0. So something's going to infinity somewhere, I'm guessing. So divide our line here with our 3 critical numbers. I'm going to pick values in each one of those segments. Start plugging them in. So when I put a negative 2 in there, I've got a negative number raised to the 5th power. So that's going to be a negative number, negative 32 times 2. So negative 64 plus 4, that's going to be negative. On the bottom, I've got positive because anything to the 4th power is positive except 0. So I know my first piece out there is decreasing. I stick a negative 1/2 in, watch what happens. Negative 1/2 to the 5th power is going to be negative 1 over 32 times 2, so negative 1/16. Take away, add 1. So positive. So I know my middle piece is increasing, one of them. I put a positive 1/2 in there. This flips the numerator. And when I put a positive 2 in, I've got 2 to the 5th is 32 times 2 is 64. Take away 4, so big positive number. And the bottom's still positive, so I've got that. Which tells us
Are you writing for mine?
yes. I've been practicing. Actually, I had this set up to make videos, but and finally, we can say this. Don't just blithely go through here and go, well, at 0, we must have a maximum. No, we don't. Because at 0, this thing's not defined. And how did we figure that out? Well, from right over here. So don't get lulled into thinking, oh, I can just sleepwalk through this. No, you can't. Not on these rational ones where the denominator could be 0. And since they didn't give us an interval, we got to assume that we have to deal with this like that. So we've just got 2 relative minimums. What timing? Tomorrow, y'all.